lecture 10, we were talking about two important concepts. Unification was there, most general unifier, and then we did some examples related to how to find a most general unifier working out by hand. So, and as I told you earlier, once we start seeing the programming language, then probably these all will make sense much better. So I still had to cover one more portion last time, which I actually left out, but that it is there in the slides. So before getting into that, let us just brush up what we saw in the last class. So these were the kind of examples given to you, and you were asked to apply certain rules. I had given everything in an algorithmic fashion, and you applied those rules and you tried to find the most general unifier. And it was told in one of the slides that if you apply this procedure, then you are definitely going to find an MGU if there exists one. If it doesn't exist, then your program should come out telling that the most general unifier does not exist. So, yeah, that was the gist of previous lecture. Today we have to probably learn one of the most important concept as far as programming in logic is concerned, or programming in Prolog is concerned, because other programming languages are also there where these things are what you call overruled. So as far as the language Prolog is concerned, you have to also learn one more concept, which is called occur check. It is pretty much the same as what we saw for most general unifier, but a slightly different concept. Let us see what it is. So as in the previous class, you are given two terms, T1 and T2. The idea is to unify them and to find the most general unifier. Now, the question is there anything wrong with this unification or with this question as such? So what you did in the previous classes, you are given two terms T1 and T2. For example, here f of x comma a is equal to f of g z comma y, and then this is the second term. So two terms are given and you try to unify them. Two ways I showed you how to do that. One was having the left hand side equal to the right hand side, and the other one was following certain 6 steps in the algorithmic procedure. Either way, you will get a most general unifier. And then, by whatever rules which are existent, you were trying to solve the problem. Now, here also I'm giving you two terms, T1 and T2. Now, if someone can tell me, is there a problem with this unification, or how will you try to unify this? Once you find the answer for this, then probably you understand the concept of occur check as such. Can anyone try to unify these two terms? T1, x likes y. T2 is g of y likes f of x. Because as far as the exams are concerned, you will be given only two terms and I'll be asking you to find the most general unifier. Any idea? You have to find the most general unifier for these two terms. Okay, let me go forward. So basically, the first procedure which we talked about in the last class, left hand side is equal to right hand side. So I am writing the first step as S0 and I'm showing likes xy is equal to likes g of y comma f of x. So probably the first substitution is an empty set because you have just started. Now you can remove both the predicates. Here the predicates, both one is likes, the other one is also likes. If they were different, then probably you would have stopped your algorithm there itself. So x is equal to g of y. The first part of the first term, you are linking it with the first part of the second term, g of y, and the second part of the first term with the second part of the second term. So like that, x is equal to g of y, y is equal to f of x. Now you are doing a substitution. You are replacing x with g of y. As I told in the previous classes, x is a variable, so you can replace it with a term. A term could be a function, a term could be a variable, a term could be a constant, things like that. So here it is g of y is a function, so I am replacing x with g of y. There is no problem with that. So now with that substitution, the second step, S2 becomes, with the first substitution W1 applied to S1, it will become G of Y is equal to G of Y. Y is equal to, since X was replaced by G of Y, Y is equal to F of G of Y. So this Y is equal to F of X is given, but F of X you have already told is G of Y. So Y is equal to F of G of Y. Now at least can you see, is there a problem happening, or how can you actually go ahead and solve this? This is pretty much straightforward. I mean, there is nothing complicated in this at all. Two terms are given. You are telling that the first term is the left-hand side and the second term is the right-hand side, and you are telling that both of them are equal, because that's the idea of a most general unifier. Eventually, you show that the first term is equal to the second term after some substitution. So here also I am substituting pretty much the same way we did for the other examples. Now, can anybody tell me what could be the end result of this unification? X is replaced with g of y, so you get g of y is equal to g of y in the first term, and y is equal to f of x. X you replace with g of y, so you get y is equal to f of g of y. Most of you have done programming. Will something go wrong here or not?
Sir, it will enter into an infinite loop kind of thing.
Sorry?
It will enter into some kind of loop.
Why? That is correct what you told. It'll enter into some kind of loop. That is what she was telling, so which is correct. So why, and what is the reason is, y occurs in a term containing it. So g of y, x you have replaced with g of y, but y again you are telling is f of g of y. So this y occurs in a term containing it. If that sort of thing happens, then there is something which is really nasty going to happen as far as programming is concerned, programming in logic is concerned, and that is what I have explained below. An equation that has a variable on one side and a term containing that variable on the other side. So here you have a variable on this side y, and here on the right hand side you have a term, because it's a function, so it is a term f of g of y, and on one, and a term containing that variable on the other side cannot be solved no matter what the substitute is. So if you try to do the unification, it goes on. So first it becomes f of g of y, then again it becomes f of g of y, again something, 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 it goes on. So the unification fails. I mean, it doesn't fail. Basically, it goes on forever. As somebody was pointing out, it goes on as a loop. The above phenomenon is called occur check. In all Prolog systems, for efficiency reasons, occur checks are not performed. They simply go ahead. Okay, there is something below. I think that's an error, but what it means is they simply go ahead to generate solution. That means they might go one step, two step, three step, four step, and they will halt and tell, look, this is the substitution you are getting, but actually that is wrong. That is not the substitution, but then somewhere you have to stop. You have to either stop in the third step or the fourth step or the fifth step. Otherwise, you'll keep going. So basically, what it says is that Prolog is not a faithful implementation of first order logic. Because if it was, since you are trying to capture the whole of first order predicate calculus using a programming language, you enter up with such problems. And hence, the programming language as such is not a complete implementation of the actual mathematical apparatus which is lying below. But anyway, we guys are interested in the computing part. So basically, we are not much concerned about the probably the mathematical complete, but that is actually not the right way to do. But that is how the programming language is set up. So occur check is probably one of the last important concepts you have to know. And now we come into the logic programming part. That is your what you call the practical aspect. But in that also you have to see certain resolution, because I stopped with resolution. So I'll take a few slides on this and then go back to resolution. But you need to see, because till now probably since the programming part was not there, it might be a little bit cumbersome for you to understand. But let us for today, let us see how these things actually work out. So we are getting into, so all of what we have learned till now is carried forward in the in the programming part also. You were doing everything by hand, but now you can use certain language to code this up. That is the difference. So a logic program corresponds to a set of first order sentences. And what is the set of first order sentences? You already know. I am denoting it with that symbol. Submitting queries. So since you have a knowledge base, you have facts and rules, you need not write another program to find an answer. You need to write a program, but you can write that program in the form of questions or queries, just like in a database. So submitting queries. Submitting a query phi, which also corresponds to a sentence, to a logic programming system means asking whether phi can be derived or inferred from the information given in the program that let us call that delta. That is whether phi follows from delta. So this is really different from the database part, because in database part you don't do any inference. Or in other words, either you can ask whether delta satisfies phi or phi follows from delta, or whether delta union negation of phi is unsatisfiable. So delta union negation of your query will end up in a contradiction, then that is also correct. So there are a couple of ways to find the answer. Whereas in the SQL, there is only one way. You don't take the negation of the query and submit and then find a contradiction and then find the answer for your tuple. No, it is pretty much straightforward. So logic programming is an application of automated deduction, and Prolog is a logic programming language which extends this basic idea with additional control structures. For example, negation as failure and cuts. Cut will come towards the end of the whole lecture. So in the prologue part, negation as failure, you already know, it is proof by contradiction basically. Programs in pure Prolog can be translated into first order logic. That is the relation between these two. Prolog rules of, actually this is the form. So there is a Q I have given here, 2 dots and a hyphen I have given here. Basically, that 2 dots and a hyphen means an arrow. It is an arrow of this sort. But in the Prolog syntax, there is no arrow. The syntax used for an implication is a 2 dots and a dash. So how do you read that? Prologue rules of the form Q if P1 to Pn. Yeah, so there is a difference also here, because once you give a right-handed arrow, it actually means if then, but in the prologue language, it actually means the other way. Then if you please keep this in mind, this is very crucial. Once you write a rule of this form, Q, a two dots and a hyphen is given, and P1 to Pn, then this actually means that Q if P1 to Pn. Or if you have to read it the other way, then it means if P1 to Pn, then Q. So the arrow is actually the other way, it is going the other way around. And this is very crucial as far as the prologue syntax is concerned. So I have written the translated form also. Q if P1 to Pn are translated as for all x1 to xn, P1 and P2 and P3 and Pn, then Q. So it is coming the other way around. When you read the textbook also, that might be slightly confusing. That's why I am stressing it out here, where x1 to xn are the variables appearing in the rule. That obviously you know that. And you can also find that in this format, all the universal quantifiers are coming in the front, which is obviously called as the pre-next normal form. Now, that is the rule form which is given in the beginning. Prologue facts of the form Q is again translated something similar for all x1 to xn Q, where x1 to xn are because a fact can also have a variable, right? I mean, John of x, or father of x, could that x can actually take in John or Peter or anything like that. Or else it can be a simple, straightforward name itself. So it can be either one of them. So prologue facts of the form Q is translated as for all x1 to xn Q, where x1 to xn are the variables appearing in the fact. And when you try to ask a query or a question, how is it translated? Prologue queries of, and that question mark is coming because that is the prompt which actually comes in the prologue. When you try to invoke the prologue interpreter, it is just like the Unix system. But in Unix, you have a dollar, but here you have a question mark. It is just waiting for your question to come up so that it can answer. And a question mark and a hyphen, that is what it means. So prologue queries of the form P1 to Pn are translated as for some x1 to xn. That means at least, is there at least a single answer which you can provide, such that P1 and P2 and P3 to Pn, where x1 to xn b are the variables appearing in the query. So the negation of the query has the form. Since negation happens with the existential quantifier, it turns out to a universal one, and the negation is pushed inward, and you will get P1 to Pn. And one observation you can do in this given slides is that all the above formulas correspond to Horn clauses. Horn clauses, you know, what is a Horn clause? At most, probably you forgot, one positive literal. So all the above formulas correspond to Horn clauses. In fact, rules and facts correspond to positive Horn clauses, and negated queries correspond to negative Horn clause. That is what it means. It will become clear once we do that particular example. So two slides related to logic programming. One is seeing programs as a set of rules and facts, and the second one is how it gets converted into first order logic. Okay, pause. I thought I had covered this earlier. So positive Horn clause means one positive literal, and negative Horn clause means no positive literals. This you have to keep in mind. Now, when it comes to prologue, it implements something called as SLD resolution. Resolution we will be seeing in a short while. SLD means selective linear resolution for definite clauses. So you have to know what is linearity, what is definite clauses, etc., etc. Linearity means we start with the only negative clause. So here the negative clause is the negated query. And then always use the previous resolvent. So once you have applied the negated query to the set of facts and rules you are having, you obviously get certain offshoots of that, which are called the resolvents. When I tell offshoots, it means the negated query gets cancelled with the positive part of some fact or rule, and whatever is remaining is the resolvent. So we start with the only negative clause and then always use the previous resolvent, that is a new query. The forward chaining and backward chaining example which we saw in one of the classes, it is exactly or pretty much the same. The selection function is very simple. It always chooses the first literal in the current query. Input is restricted to one negative horn clause, that is the negated query, and there will be a lot of other positive horn clauses. Now backtracking, as you always know, so you start with the left branch, you get stuck somewhere, then you move back up the left branch, then you come down again, try to find some positive query to cancel with, like that. So backtracking is always there as far as Prolog is concerned. In practice, one problem remains. If there is more than one way to resolve with the selected literal, that is more than one matching rule or fact, then we don't know which one will eventually lead to a successful refutation. So in Prolog, always the first one is chosen, and if this turns out not to be successful, backtracking is used to try another one. All these examples we'll be seeing once we learn the programming part. Now, one simple example I have given here, a very commonsensical one. Probably you can try to do this or note it down. It has only 4 lines of code. This is just like a code. You may not believe, but you can just cut and paste this in a file, and it should give you an answer. So I have written here, parent is the one which is outside, and inside the brackets I have given 2 names, Elizabeth and Charles. So it could mean that Elizabeth is the parent of Charles, but in some books it has been it will be interpreted the other way. So instead of interpreting Elizabeth is the parent of Charles, it would be mentioned as the other way. I mean, Charles is the parent of Elizabeth, but we'll stick to one. So the first one which comes, we will interpret that way. Elizabeth is the parent of Charles. Charles is the parent of Harry. And then 2 rules you have given. X is the ancestor of Y if X is the parent of Y. So that is how you read that. It is not the other way around. If X is the ancestor of Y, then X is the parent of Y. It doesn't come that way. X is the ancestor of Y if X is the parent of Y. X is the ancestor of Z if X is the parent of Y and Y is the ancestor of Z. Now, what will happen if we submit the following query after the above program has been consulted by Prolog? Now, the query you are giving is Elizabeth the ancestor of Harry? Now, you guys can try to answer that and tell me commonsensically, is it true or not? Then we'll see the proof procedure. Can anybody tell me what will be the answer? Is Elizabeth the ancestor of Harry?
Yes, sir.
Yes. Okay, so let us see the, maybe before that, just I'm just typing in something, a file. I'll just copy this in. I don't know whether from the PDF, let us see. We'll see this later. Yeah, probably it is coming up. So what I have done is I have written something like prolog1.pl. You can see the screen or what? Maybe not.
We can see the presentation, sir, not the
Presentation, no, okay. That is okay. So then I'll show the what you call. Okay, no, I think probably you can see it now only again. Hmm. So just see it. Now you can see the one window, right? I have typed in
Yes.
something which is called prolog1.pl. Can you see it?
Yes, sir.
Yeah. So I have just copied that whatever I have shown you in the previous slide, and I have put it in a file called prolog1.pl. It's a new file, 4 lines. You can see what is written. Okay. So let that be there. Again, we will shift back to our previous presentation and see the what you call the proof, and then come back to this. Okay. So this is the program I copied. And somebody told me that this query holds true. Let us see whether that is the case or not. Very simple example for you to understand. So is Elizabeth the ancestor of Harry? Now, from what all you have studied in the previous class, we'll try to formalize this. So instead of writing the full predicate, Elizabeth is the parent of Charles, I am just putting a capital P for ease of understanding. And for Elizabeth, I have put E, and for Charles, I have put C. There is nothing wrong with that because obviously I can format this way. Similarly, for Charles is the parent of Harry. Now see the third one. The third one says that if X is the ancestor of Y, then X is the parent of Y. Now this is a universal truth, because as long as you are the ancestor of somebody, obviously you have to relate it, you have to be related in some way, right, in your family tree. Otherwise you cannot tell you are the ancestor. So that is a kind of universal truth which is happening, and that is why I have mentioned here as a first order predicate statement. Now, since two variables are there, X and Y, to denote the ancestor as well as the parent. So this is why I was telling you it is very crucial you learn how to translate from the natural language to first order sentence. So I have translated that for all X, all Y. If X is the parent of Y, then X is the ancestor of Y. When I translate into first order logic, see how the arrow thing is happening. It is going the implication way. Whereas in the prologue part, we wrote it as the two dots and a slash, which is interpreted in a different way. Those who are not attending today's class, you please go back and explain to them. They cannot miss class. That is the one important thing I forgot to mention. If you miss one, it will be very difficult from now on. And similarly, can you tell me how do you formalize the last rule? Obviously, you have been given X, Y, and Z, so you actually need three variables there. And that is what I have done here. For all X, all Y, all Z, X is the parent of Y, and Y is the ancestor of Z, then X is the ancestor of Z. Okay. Now, the question is, the query here is Elizabeth the ancestor of Harry? Now, as I told you, or as we have done earlier, you actually take the negation of the query. So you are telling that it is not the case that ancestor Elizabeth Harry, or Elizabeth is not the ancestor of Harry. The above query is very simple. In the general case, the translation of a query is the universal closure of the negation of the conjunction of the subgoals of the query. That is okay. We'll come to the much complex queries later, but now it is just a simple query I have given, and all this is set right. Okay. Now you have to tell me how will you go and solve this. From English, you have translated to somewhat a very liberal way of first order logic translation. Now, can anybody tell me what is the next step you will do? You have to find an answer for this. No, what could be the next step? Look, you have got the negation of the query and you have got four statements there. Two are facts and two are rules. Now, suppose I give you this problem, what is the next step you need to do? From what you have
Sir,
learned in the previous class. Yeah, sorry.
we can try to solve it using resolution or other techniques that we use.
But before that, you need to do certain things, no? All x, all y, p x y, a x y, all x, all y, all z, p x y, a y z, a x z. Okay, so formulas we get from translating a prologue program already are in pre-next normal form, and we don't need to columnize either. So two things are coming for free. Actually, all these things we learned in the previous class. First is pre-next normal form, then columnization, etc., etc. But this slide is telling that translating a prologue program already has been columnized as well as in pre-next normal form. Only thing you have to do is to rewrite the implications as disjunctions. So that is what I was expecting from you, because you need to get rid of those arrows. Otherwise, it doesn't work. You have to change it into a clausal form. That's what I meant. So we have to rewrite the implications as disjunctions. Here we directly give the clauses which correspond to disjunctions, and the variables have to be renamed. That is another most important thing you keep forgetting. Last class also it was pretty much the same. So let us see the first two, PEC and PCH. You pretty much put it like that, 1 and 2. 3 you see, all x, and since it is a universal quantifier, you can pull both of them out. If pxy, then axy becomes not px1y1, because you are renaming the variables. X and y is happening in the first rule as well as the second rule. So you need to keep track of which x and y is happening with which rule. That is why you are renaming the variables. So you are putting x1, y1 there. Similarly, since for the other xy also, as it is happening in the same rule, negation remains as such. Then you are coming to the fourth rule. Again, there is an x, y, and z happening there. To keep track of that x and y, you are renaming it as x2, y2. And it could happen, you can rename it as z1, but I kept z2 to have to make sure that that z is happening with the second rule. That is why. Okay. And then the negation of the query comes as it is. Okay, now you do and tell me. Yeah, somebody told that you can apply resolution and come up with a solution. Okay, what could be the solution then? Now it should be clear to you. Resolution means you cancel out a positive clause with a negative clause. You can see that all these are in clausal form, so there is nothing to worry about it. You just have to find the positive one with the negative one, cancel it out. Only problem you will be facing is that there is some variable happening, there is some constant happening. That is all. But that you should be able to do it, isn't it? Anybody? No. Okay. So see this. I have written down the same one. 6 is, yeah, okay, you can tell. Okay, anyway, I've given the answer. not P E Y3, not A Y3H from 4 and 5. It is self-explanatory. So in 4 there is a negation of, there is a positive A. In 5 there is a negation of A. So A x2 z2 is there in the 4th clause. In the 5th clause there is a negation A he H. Now x2 and z2 are variables, E and H are constant. So E gets transferred to x2, that is what I have shown here, and H gets transferred to z2. Now when these two gets cancelled, what is remaining? Remaining is negation of P, and x2 is already replaced with E, so you put y2. Why? I have again renamed as y3 because it is a different clause, and I want to be, I want to show that this y3 is happening after a resolution step has happened. So y3 I have got as part of a resolution step. It is a resolvent which has happening with 4 and 5. It is a resolvent of 4 and 5. So I am renaming. But if you are smart enough, you can keep the same variable name y2. But eventually in a long program, you tend to get confused with which variable you used where. So since to denote that this is a resolvent of two other clauses, I am renaming this y2 as y3. Now next, again, this clause will remain. So that negation A is there. Y2 already I have renamed as y3, and Z2 as such, the constant H is given to Z2. So you get not A y3H. Now I think you should be able to do the rest. C7. Not A C H. You have taken 1, now you have taken 6. 1 has a positive P, 6 has a negative P. E and E is the same. So Y3, you substitute Y3 with C, and then what you get is not A C H. So here Y3 you get C, and then you get the H, not A C H. Now can you complete that? Okay. What is the next step? You guys are there, right?
Yes, sir.
Okay. I am putting not P C H from 3 and 7. So 3 has a positive A, 7 has a negative A. Positive and negative gets cancelled. C is passed to x1, H is passed to y1. So you get not PCH. So remember, you started with a negation of your query. So you have to eventually get a contradiction which tells that the positive query is true. The negation which you have taken is ending up with contradiction. That's the idea. Now, not PCH cancels with positive PCH from 2 and 8. So there is a contradiction, and which actually means that Elizabeth is the ancestor of Harry. You started with the 5th telling that Elizabeth is not the ancestor of H, and you ended up with a contradiction which means Elizabeth is the ancestor of Harry. If there had been variables in our query, then the substitutions made to them would have been part of the answer. So this is how, a first order resolution works. Now, I have slides only till here, but I have other slides from the original sir. But before getting into it, to alleviate how these things work out as far as programming language is concerned, I'll just take you back to the previous slide. So it is the same example here, but I'll show you how these things will work out as far as a uh, programming language is concerned. Where is the other? Yeah. Okay. So this window in which I have written something. You can see it, right? Okay, I did a mistake.
Yes, sir.
So what you can do is, I'll probably blow up a bit more. Why the hell I'm not able to? Oh no, okay. This is weird. Arey, what am I doing? Okay. Actually, I could blow this up. Are you able to see it? No problem, no? You can visualize what I've written.
Yes, sir. It's clearly visible.
Okay, so that is a particular, I mean, whatever I showed you in the slide, I have written it. You are able to see, right?
Yes, sir. We are able to see that.
Yes, sir.
Okay. So now, same another window I have opened here. I'm in the same directory. So what you can do is you can go back home and download something called as gprolog. So that is what we will be using. So once you download and install that, you will get and you try to run, you get something, a prompt of this type: copyright 1999 to the Daniel Dias. Okay, and you can see a question mark and a hash. This is what I was telling you earlier. And
Sir, we
now
are able to see only one terminal.
so this program has there's only one terminal. Oh God. Again, I have just opened it now. Oh, I think I can share only one terminal, isn't it? Okay, no problem. You can see it now, right?
We are able to see the code
Okay.
terminal, sir.
Only code, huh?
Yes, sir.
Okay. Okay. Now?
Now we can see it.
Now you can just see you can't see the code, right?
No, sir.
Okay. So code. So let that code window be there in your mind. Now what you have to do is you get a Unix window like this. You have to download gprolog as I was telling you, and then once you install that, you can actually write these things down, G prologue, and then you get a copyright 99 Daniel Dice. Okay. Now, earlier, what I showed is that I have written a code called prologue1.pl in which that small 4 lines of code is there. Now, you call that. You call two square brackets and prologue1. Name of it was prologue1. You can see that it is compiling. In my desktop, I have that prologue1.pl and 4 lines read and how many milliseconds it has taken. Now, what is the query you asked in that question? Do you remember? We had a query, right? One question we asked. Immediately forgot.
A
Short
of
term
E,
memory.
H.
Is Elizabeth the ancestor of Harry? Isn't it?
Yes, sir.
No, but because in the code, we gave the full thing. We did not formalize it into A and C. You remember? So you have to ask the full one. So basically, you have to ask, is Elizabeth, probably the names have, I mean, the words have to be the same. See what is happening. Is Elizabeth the ancestor of Harry? It is telling true, and a question mark is coming. It is actually waiting because you want to ask more questions. If you do not want to ask more, that again you press your enter button and it has come out of the interpreter. So what basically you are doing is G prologue is a prologue interpreter, but there is also a compiler. Like the GCC, there is also a compiler available that you can go, and if you want to use that, you use that. If you want to use the interpreter, you use the interpreter. There are many versions of Prologue also. SWI, I don't know, Sixters, lots are there. G Prologue is the one which is being often used by most of the universities. So this is a natural language kind of interpreter, basically. Now, if you want to see how these things are done in the background, that also you can have it now. You can see the answer right now. Elizabeth ancestor Harry, it is giving true. Now, if you want to see how all this is being done in the background, there is a command called trace, which means you are tracing the whole execution. You give trace, then you give the query. So now it goes one by one. It wouldn't give you the answer immediately as you saw in the previous step. In the previous step, it was given true. But here, after trace, you can see something is written. The debugger will first creep, showing everything. So now you can see the calls. How the call is happening for that 4-line call. First, it is calling, is Elizabeth the ancestor of Harry? Then it is calling, is Elizabeth the parent of Harry? There it is failing because there is nothing which shows that Elizabeth is the parent of Harry. Why? Because the facts which were given to you, in that Elizabeth is the parent of Charles is shown, but not Elizabeth is the parent of Harry. That I'll show together. Okay. So, okay. So no trace. Now together I will show. Let us see that prologue code also so that you will understand. This was the code written. Okay. Please see carefully. This was the code written by you guys. So here, Elizabeth is the parent of Charles. Charles is the parent of Harry. I have written together. That is okay. So this was the first fact. Elizabeth is the parent of Charles. Second fact is Charles is the parent of Harry. Third is a rule. X is the ancestor of Y if X is the parent of Y. Fourth was X is the ancestor of Z. Then if X is the parent of Y and Y is the ancestor of Z. Now what you did is you are asking a query, is Elizabeth the ancestor of Harry? Now that query is the first call. Second call is Elizabeth the parent of Harry? Then it is failing. Why? Because Elizabeth is not the parent of Harry, is not there in your knowledge base. Elizabeth is the parent of Charles, is there in your knowledge base. And Charles is the parent of Harry, is there in your knowledge base, but not Elizabeth is the parent of Harry. That is why it is failing. So it fails. Second one, it fails. Then it backtracks. Is Elizabeth the parent of, there is one underscore 342. Underscore 342 means Prolog is internally assigning a variable to X or Y, which you might have given X or Y as variable, but when Prolog internally assigns, it often assigns every variable with an underscore and a number. So the X and Y which you have given is for the Prolog interpreter to understand. It will initialize it into some internal way, that is underscore 342. Is Elizabeth the parent of some X or Y? Yes, Elizabeth is the parent of this. Is Charles ancestor of Harry? Because based on the rule, I'm not able to show both. Why? Because in the first rule you have X is the ancestor of Y if X is the parent of Y. That it failed once. In the second rule you have X is the ancestor of Z if X is the parent of Y and Y is the ancestor of Z. Now it has to satisfy these. That is why that rule is being called twice. Unfortunately, I'm not able to show both together. So the first one fails at some point, whereas the second rule is succeeding. It is calling that head part and the tail part is that I will explain once I come to the programming. Today, and that being rule and the and eventually out loop. So this is how in actual Prolog programming language things work from a natural language perspective. So whatever you are learning, if you are trying to build up a what you call kind of application, it works well. But this is only the reasoning part. When we get into learning, you can see there are many machine learning techniques available to actually handle NLP problems, but they fail to incorporate this reasoning part. This is what I have been learning from the first class. Because there are not many groups who are specialized in, it's impossible. So the more you like to combine the reasoning plus using what is it called? One is like summarization. One is summarization. So it is only the machine learning techniques which are being applied. The reasoning part we have not to incorporate much. So understanding this, incorporate interested in some kind of will help you. That use is logic programming. What is the art programming? If you are interested in, so I'll continue with the resolution part class. I think probably I'll get some more time. Again, from Monday to Saturday, 1 hour we'll be having. I want to cover up for the lost classes also. And I will go resolution theory plus the application also of this time. Okay. So I'll stop here now. If you have any questions, queries, you can ask.
Sir, the recorded video